Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to material science and engineering. Previously we discussed the basic introduction to elastic and plastic behavior of solids. So in this video we are going to extend that discussion and we'll discuss specifically about the elastic behavior. And we'll try to understand it in terms of the interatomic forces and potential energy between the atoms. So just a quick review that any rigid body which has a definite shape and size, it can be altered in its shape and size and its dimension through the application of an external force, and that external force is called as deforming force, and this process is called as deformation. So this change in shape and size, it's either temporary or permanent. In case it is temporary and the material, it returns back to its original shape and size after the removal of the deforming force, that is called as elastic behavior, and the property is called as elasticity. And in case the deformation is permanent and the deformed body, it does not return back to its original shape and size, that is called as plastic behavior, it is called as plasticity. Okay. Now here our main focus is the elastic behavior. Okay, the elastic behavior, elasticity. So how we can explain this elastic behavior of materials? Let us say we take an object, a body, a rigid body, let's say. Now we can visualize it as consisting of atoms with a well-defined geometry, with the atoms placed at different points, okay, like this, in a three-dimensional space. Now each of these atoms, they are separated by a certain distance, okay, in the stable position, in the equilibrium position, in the absence of any external deformation force. When the body is there present, its shape and size is fixed, and this is because of the fixed position of the atoms. Each of these atoms, it is separated by a certain distance, which is called as the interatomic separation. Okay, now there is this concept of equilibrium separation distance, okay, where the interatomic force between the atoms is zero. There is no force of repulsion or no force of attraction. And this separation distance at which the interatomic force is zero, that is called as the equilibrium separation distance. Equilibrium separation distance. And in this case, the potential energy between the atoms is minimum. It is negative, but it is minimum. Now, there are three cases here. Okay. Suppose because of the externally applied force, the separation distance, it increases. Okay, the separation distance increases. That is, it becomes greater than the equilibrium separation. Okay, the separation distance, it becomes greater than the equilibrium separation. R is greater than R0. In that case, the interatomic force is attractive in nature. Okay, so the two atoms, they are separated by a separation distance which is greater than the equilibrium separation. In that case, the interatomic forces, they are attractive in nature. Each tries to attract the other atom towards itself, and the potential energy is negative, the potential energy between the atoms. So here the interatomic forces, they try to restore the atoms to their original equilibrium separation, because we are discussing the elastic behavior. So when the interatomic forces, they attract each other, they are basically trying to restore the atoms to their original position, that is the minimum potential energy, zero interatomic force, equilibrium separation position. Okay. Now the other case, when the separation distance is lesser than the equilibrium separation. Okay, when the separation distance is lesser than the equilibrium separation, that is R is lesser than R0. In this case, the interatomic forces, they are repulsive in nature. Each atom tries to push the other atom away. Okay, each atom tries to push the other atom away from it. So basically here also the interatomic force, the repulsive interatomic force, tries again to restore the atoms back to their original equilibrium position. Suppose the interatomic forces, in this case, let's say this is the equilibrium position. Let's say the two atoms shift to this position. So in this case, the interatomic forces will be attractive in nature. It will try to return the atoms back to their original position. So this is R greater than R0. Suppose the two atoms again move back to this position. Okay, here. R lesser than R0. In this case, the interatomic force is repulsive in nature. Again, trying to restore the two atoms back to their original stable equilibrium position. R is equal to R0. So here, the main thing to remember is that every material, every object in this universe, that is the elastic object we are talking about, okay? The elastic object, every elastic object, the atoms in their stable equilibrium position are separated by a fixed separation gap. That is called as the stable equilibrium position. Okay, it is called as the normal or equilibrium separation R0. And in this case, the potential energy is minimum and the interatomic force is 0. Only when an external force is applied and the material undergoes deformation, then the two atoms, they are either the separation gap either becomes greater than R0 or lesser than R0. In that case, the interatomic force acts, whether it can be attractive or repulsive depending upon the separation gap, and the objective is always to return the two atoms back to their equilibrium separation. When they go away, the interatomic force is attractive in nature. It tries to pull the two atoms back to their original position. When they are very close, that is the equilibrium separation is, the separation is lesser than the equilibrium separation, the interatomic force is repulsive in nature. It tries to push the two atoms back to their original equilibrium position. Okay, so this is the elastic behavior of solids. Okay, the objective is always to return back to their stable equilibrium position. So that is why elastic materials always return back to their original shape and size, because of the interatomic forces. Whether they undergo deformation, whether they are stretched, compressed, bent, whatever it is, it leads to change in the separation gap between the atoms. So depending upon the magnitude of the separation and the nature of the separation, attractive and repulsive interatomic forces act to restore the atoms back to their stable equilibrium position. Okay, the objective is always to restore the atoms back to their stable equilibrium position. Okay, this. So this can be visualized in this way. Let's say we have this object. It has atoms which are separated at fixed equilibrium distances. In the first case, the external force takes the atom away from each other. So the separation becomes greater than the equilibrium separation. In this case, the interatomic forces is attractive in nature, and here the interatomic forces, they are opposite in direction to the external deforming force. This is the deforming force, external deforming force, and this is the interatomic force. They are opposite in direction. Okay, so the interatomic force, it restores the two atoms back to their original equilibrium position. Same thing happens but in the opposite direction. When the external deforming force, it brings the two atoms closer, that is the equilibrium the separation gap is lesser than the equilibrium separation. Here again the interatomic force acts in the opposite direction to the external deforming force and returns the atoms back to their original equilibrium position. Okay, so in all of these cases, no matter what the direction of deformation is, the interatomic force of attraction and repulsion always act in the opposite direction to the external deforming force and always restore the atoms back to their original position. So the initial and final separation is the same. This is temporary. This is temporary. Here also same. Initial and final is same. This is temporary deformation. Okay, so this can be understood with the help of a potential energy versus separation gap graph, or a force, interatomic force versus separation gap, interatomic separation R graph. So here we have taken a XY plot where U is in the y-axis, which is the potential energy between the atoms, and R is the interatomic separation between atoms. So as you can see, when this side, when this is R greater than R0, when the interatomic separation is greater than the equilibrium separation, the potential energy is mostly negative. It is negative, okay, like this. And here this is the minimum potential energy position, which is the stable equilibrium position. It is negative and minimum potential energy position. Once the equilibrium, the interatomic separation is lesser than R0, the potential energy increases very suddenly and sharply. It becomes positive. Okay, this is potential energy versus interatomic separation graph. Same can be done with the same nature for the interatomic force and interatomic separation graph. So here, from here to here, the interatomic separation is greater than the equilibrium separation distance. So it is, the interatomic force is negative, but it is attraction, which basically represents attractive nature. The interatomic force is attractive in nature. Okay, now once the equilibrium, the interatomic separation is lesser than the equilibrium separation, the interatomic force, it becomes repulsive in nature, which is a sharp increase in value. It becomes positive and increases sharply. So the nature of both the graphs is the same, whereas it remains at a certain value where R is greater than R0, okay, negative value, and there is a sharp increase when R is lesser than R0. Okay, R is the interatomic separation, U is the potential energy, and F is the interatomic force. Okay, so this is basically the explanation of elastic behavior of materials, which is the tendency of the materials to return back to their original shape and size on the removal of the external deforming force. The deformation is temporary in nature. So how we can explain such a behavior? In terms of interatomic force and potential energy. Okay, so this is the thing.